acting with a pseudorandom function. Okay, and we're going to come back actually later on and define PRFs more precisely. But for now, I wanted to give you the intuition for what it means for a PRF to be secure, so you'll understand what it is that we're trying to construct when we construct these pseudorandom functions. And I should say that the definition for a pseudorandom permutation is pretty much the same, except instead of choosing a random function, we're going to choose a random permutation on the set X. In other words, a random one-to-one function on the set X. The adversary can either query this random function on the set X, or he can query a pseudorandom permutation, and the PRP is secure if the adversary cannot tell the difference. Okay, so again, the goal is to make these functions and permutations look like truly random functions of permutations. Okay, so let's look at a simple question. So suppose we have a secure PRF. So we know that this PRF F happens to be defined on the set X, and it so happens, it outputs 128 bits every time. It so happens that this PRF cannot be distinguished from a truly random function from X to 0, 1 to the 128. Now we're going to build a new PRF. Let's call this PRFG. And the PRFG is going to be defined as follows. We say if X is equal to 0, always output 0. Otherwise, if X is not equal to 0, just output the value of F. So my question to you is, do you think this G is a secure PRF? Well, so the answer, of course, is that it's very easy to distinguish the function G from a random function. All the adversary has to do is just query the function at X equals 0. For a random function, the probability that the result is going to be 0 is 1 over 2 to the 128. Whereas for the pseudorandom function, he's always going to get 0. Because at 0, the function is always defined to be 0 no matter what the key. And so all he would do is he would say, hey, I'm interacting with a pseudorandom function if he gets 0 at X equals 0. And he'll say, I'm interacting with a random function if he gets non-zero at X equals 0. So it's very easy to distinguish this G from random. So what this example shows is that even if you have a secure PRF, it's enough that on just one known input, the output is kind of not random. The output is fixed. And already the entire PRF is broken, even though you realize everywhere else the PRF is perfectly indistinguishable from random. Okay, so just to show you the power of PRF, let's look at a very easy application. I want to show you that in fact pseudorandom functions directly give us a very simple pseudorandom generator. Okay, so let's assume we have a pseudorandom function. So this one happens to go from n bits to n bits. And then let's define the following generator. Its seed space is going to be the key space for the PRF, and its output space is going to be basically t blocks of n bits each. Okay, so you can see the output is a total of n times t bits for some parameter t that we can choose. And it turns out basically you can do this very simple construction. This is sometimes called counter mode, where essentially you take the PRF and you evaluate it at 0, you evaluate it at 1, you evaluate it at 2, at 3, at 4, up to t, and you concatenate all these values. That's the generator. Okay, so we basically took the key for the PRF and we expanded it into n times t bits. Okay? A key property of this generator is that it's parallelizable. And what I mean by that is if you have two processors or two cores that you can compute on, then you can have one core compute the even entries of the output, and you can have another core compute the odd entries of the output. So basically, if you have two cores, you can make this generator run twice as fast as it would if you only have a single core. So the nice thing about this is, of course, we know that pseudorandom generators give us stream ciphers, and so this is an example of a parallelizable stream cipher. And I just wanted to point out that many of the stream ciphers that we looked at before, for example, RC4, those were inherently sequential. So even if you had two processors, you couldn't make the stream cipher work any faster than if you just had a single processor. Now the main question is, why is this generator secure? And so here I'm only going to give you a little bit of intuition, and we're going to come back and argue this more precisely later on. But I'll just say that security basically follows directly from the PRF property. And the way we reason about security is we say, well, this PRF by definition is indistinguishable from a truly random function on 128 bits. So in other words, if I take this generator and instead I define a generator using a truly random function, in other words, I'll write the output of the generator as f of 0 concatenated f of 1 and so on and so forth, using a truly random function, then the output of the generator using the truly random function would be indistinguishable from the output of the generator using a pseudorandom function. That is the essence of the security property of a PRF. But with a truly random function, you notice that the output is just truly random, because for a truly random function, f of 0 is a random value, f of 1 is an independent random value, f of 2 is an independent random value, and so on and so forth. So the entire output is a truly random output. And so with a truly random function, this generator produces truly random output and is therefore a perfectly secure generator. And so you see how the PRF security property lets us argue security. Basically, we argue that when we replace the PRF with a truly random function, the construction is necessarily secure, and that says that the construction with a pseudorandom function is also secure. Okay, and we're going to see a couple more examples like this later on. So now you understand what a block cipher is, and you have intuition for what security properties it's trying to achieve. And in the next segment, we're going to look at constructions for block ciphers. So now that we understand what block ciphers are, let's look at a classic example called the data encryption standard. So just a quick reminder, block ciphers basically map n bits of input to n bits of output. And we talked about two canonical examples, triple DES and AES. In this segment, we're going to talk about DES, and we'll talk about triple DES actually in the next segment. And then I also mentioned before that block ciphers are often built by iteration. In particular, we're going to look at block ciphers that are built by a form of iteration where a key k is first expanded into a bunch of round keys, and then a round function is applied to the input message again and again and again. And essentially, after all these round functions are applied, we obtain the resulting ciphertext. Okay, and again, we're going to look at how DES, the data encryption standard, uses this format. I just want to be clear that in fact, to specify a block cipher of this type, one needs to specify the key expansion mechanism, and one needs to specify the round function. In the segment here, I'm going to focus on the round function, and I'm not going to talk much about key expansion, but I just wanted to mention that in fact, key expansion is also a big part of describing how block cipher works. Okay, so let's talk about the history of DES. Essentially, in the early 1970s, IBM realized that their customers are demanding some form of encryption. And so they formed a crypto group, and the head of that group was Horst Feistel, who in the early 70s designed a cipher called Lucifer. Now, it's interesting. In fact, Lucifer had a number of variations, but one of the later variations, in fact, had a key length that was 128 bits and a block length that's also 128 bits. Okay? In 1973, the government realized that it's buying many commercial off-the-shelf computers, and so it wanted its suppliers to actually have a good crypto algorithm that they could use in products sold to the government. So in 1973, the National Bureau of Standards, as it was called at the time, put out a request for proposals for a block cipher that's going to become a federal standard. And in fact, IBM submitted a variant of Lucifer. That variant actually went through some modification during the standardization process. And then finally, in 1976, the National Bureau of Standards adopted DES as a federal standard. And in fact, for DES, it's interesting that the key length was far reduced from Lucifer. It's only 56 bits, and the block length was also reduced to 64 bits. And in fact, these decisions, especially the decision to reduce the key length, is kind of the Achilles heel of DES and was a source of many complaints over its life. In particular, already back in 1997, DES was broken by exhaustive search, meaning that a machine was able to search through all 2 to the 56 possible keys to recover a particular challenge key. And in fact, we're going to talk about exhaustive search quite a bit. It's quite an interesting question, and there are various ways to defend against exhaustive search. And basically, this 1997 experiment kind of spelled the doom of DES. It meant that DES itself is no longer secure, and as a result, the National Institute of Standards, as it became known, issued a request for proposals for a next generation block cipher standard, and in 2000 it standardized on a cipher called Rheindahl, which became the Advanced Encryption Standard, AES, and we'll talk about AES later on. But in this segment, I want to describe how DES works. Now, DES as a cipher, it's an amazingly successful cipher. It's been used in banking industry. In fact, there's a classic network called the Electronic Clearinghouse, which banks use to clear checks with one another, and DES is used for integrity in those transactions. It's also used in commerce. In fact, it was very popular up until recently as the main encryption mechanism for the web. Of course, now that's been replaced with AES and other ciphers. Overall, it's a very successful cipher in terms of deployment. DES also has a very rich history of attacks, which we'll talk about in the next segment. Okay, so now let's talk about the construction of DES. So the core idea behind DES is what's called a Feistel network, due to Horst Feistel. And basically it's a very clever idea for building a